Well, hello everyone, and welcome to the webinar on demystifying NVMe-oF from Pavilion Data. My name is Keith Parker. I'm the Director of Product Marketing here, and I'm joined by Keith Ober, our Pavilion Data Architect, who will be discussing NVMe-oF, how it differentiates itself from NVMe, and why it's important to different workloads, different data sets, and how it can be important to really any type of environment. So with that, let's go ahead and get started. So the first thing I want to talk about today, and I won't spend a ton of time on this, but just to make sure everybody's on the same page, I want to touch just briefly about NVMe. So NVMe was really introduced to solve a challenge that was faced by SSDs. SSDs were among the first ways that flash memory was utilized to add high performance to data storage. SSDs were kind of introduced really to enable the ease of incorporation of flash memory into data storage systems. Early SSDs, the flash memory was very fast, especially compared to spinning disk, but it was very expensive and it wasn't very large. So it was typically used as a caching tier. And the easiest way to incorporate that into existing spinning disk arrays was to give it the same form factor and the same interface as those spinning disks. So it was much easier to go ahead and incorporate them. The problem was those SAS and SATA interfaces weren't really optimized for flash memory. They're great for hard drives, but when you look at the high performance, when you look at the parallelism that flash can enable, those interfaces really became a bottleneck. Especially when you add in a lot of the things that have been done to those disk protocols over the years to create better performance for disk, but it actually ended up not helping flash. It actually ended up hindering it because it added in extra overhead that didn't add any extra performance. So NVMe was really created to free flash from the overhead of those legacy interfaces. NVMe enables SSDs to operate their full potential. It unlocks the parallelism, it unlocks the high performance, it unlocks everything that flash can go ahead and provide you right up until they hit that next bottleneck, which is going to be whatever your storage interconnect is. It's typically going to be, if you're using a SAN, it's typically going to be fiber channel. It might be iSCSI. If you're using it in a network attached environment, maybe it's NFS. Whatever that next bottleneck is, that's where the problem really becomes. And one of the challenges that you run into in some of those legacy architectures is really around the queue depth. When you look at, say SAS, the high performance enterprise class disk protocol, you're going to be limited to one queue. You can have commands in a single queue, and that queue has a depth of only 256 commands. So it's very serialized. It's very much a funnel. No matter how those commands come in, they're all going to have to get into a relatively short line. If you're using a SATA interface, it's even shorter. There's only a depth of 32 commands in that queue. NVMe is able to go ahead and unlock that. It provides significantly better bandwidth. It provides 64,000 queues. So 64,000, obviously, a bit more than one. But it's not just the number of queues, it's the depth of those queues. So each of those 64,000 queues have a depth of 64,000 commands. So where in the previous one, commands would come in, the queue would get full, and then it would have to keep reissuing those commands. You never run into that with NVMe, because not only are there enough queues to go ahead and handle however many requests come in, but those queue depths themselves are broad enough that it ceases to become an issue. Wouldn't you say so, Keith?
Absolutely. The queue depth and having that parallelism is incredibly important, particularly around applications that might be latency sensitive. This is really the advantage that NVMe can bring. Just as a quick starter point is that queue depth, being able to spread out those requests, again, drives down latency. And also, at the same time, gives you the potential for even greater throughput.
I totally agree. So it's really been kind of a game changer in terms of performance that you can get from those flash drives. So that's the advantage of NVMe, but where does NVMe-oF really fit in? So when you look at those drive interfaces in a legacy SAN model, or this could be a legacy NAS model as well, what happens is data comes off of the drives in if you're using spinning disk in the SAS format, or if you're using NVMe, that would be the NVMe format. And when that data is then put out over your SAN, what happens is that data then gets encapsulated in the protocol that's being used for your network, whether it's fiber channel. In this case, I'm wrapping, SAS data within fiber channel, but it could be NVMe data within iSCSI. It could be, something wrapped in NFS, whatever it is, that data is getting encapsulated in the data transport protocol that you're using to send that data over your network to the hosts that are requesting it. And it gets encapsulated within the storage array, and then it gets de-encapsulated when it arrives at the host that requested it. And each of those processes are going to do two things. First of all, it's going to add latency because it's got to go through the process of putting the data within those protocol wrappers and then take them out again when they arrive at their destination. The second thing it does is it's going to reduce the total bandwidth. So if those protocols are adding to the amount of data that's being sent, that's packet size that is being sacrificed to your network that you're utilizing. NVMe-oF takes the NVMe protocol and extends it across the fabric. So it is an end-to-end NVMe solution. So the drives, the SSDs, the flash media, it's speaking NVMe. So is the network. So that extra latency that's added in by those extra protocols simply doesn't exist within the NVMe-oF model. So what is that doing? It's providing you with significantly greater potential bandwidth. It will allow you to use different transports. So NVMe-oF can use different transports. It can use fiber channel. It can use Ethernet. So this data can be sent over different networks. Yet it's going to dramatically reduce your latency while enabling significantly higher throughput. So those are the true real benefits of NVMe-oF. Significantly greater throughput, significantly lower latency.
And Keith, if I could add one thing here, if you're looking at it from the compute stack, just as a reverse view of things, you can actually see leveraging NVMe over fabrics allows you to actually lower the CPU workload on the clients because you're using less protocol overheads. And you'll see CPU utilization actually go down on your compute side. So you might be able to even decrease the amount of compute you have on one side because you're gaining that in the performance on that NVMe over fabric model.
Absolutely. And those are compute cycles that you can then use for your applications.
Exactly.
Which, let's be honest, that's what the compute's there for in the first place. You want your compute up, you want your compute cycles running your applications, doing your processes, doing the things your infrastructure is really there to do, not managing storage. So that brings us to really, if you're looking at an NVMe-oF deployment, one of the things you're going to have to look at is how do you want to do that? One of the great things about NVMe-oF is it can work on multiple transports. You can use it with fiber channel. You can use it with Ethernet. And one of the things you'll need to decide is which one of those things do you want to go ahead and do? And that's going to depend largely on your environment and where you want to go with it. If you have an existing fiber channel SAN and you're looking to add high performance storage to that existing fiber channel SAN, then using an NVMe-oF fiber channel storage array would make some sense. If you're looking to move forward and expand to different protocols, you're looking to use higher throughput, then you might want to go ahead and look at using Ethernet. Each of these has their own advantages and drawbacks. So when we compare the two, when we look at fiber channel, it doesn't have support for RDMA, but Ethernet does. So let me talk for a moment about RDMA. So RDMA stands for Remote Direct Memory Access, and a DMA is something that's been around for decades. It's essentially when you have a storage controller, and if you're using an old direct attached system, if you had your storage controller, it would take the data from the drive and put it directly into system memory instead of interrupting the host CPU to go ahead and perform that function. What RDMA does is it extends that ability over the network. So in this case, the storage array is able to take the data, place it directly into memory of the host system that's requesting it without interrupting either the CPU of the host system that's requesting it or adding latency over the network. So it's going to provide significantly lower latency over the network. When you look at the roadmap for these different technologies, you're going to see that Ethernet actually has a very robust roadmap going forward. Fiber channel, when you're looking at that, it is the predominant enterprise connect today into a storage network. And the most common is going to be 32 gigabit fiber channel. 64 gigabit is now available, but it's still very, very limited in its offering. But that's actually as far down the road as there is on a roadmap for fiber channel. There really isn't a plan to go too far beyond that. Ethernet, on the other hand, is, it's the most common networking technology in the world, and it has a very robust roadmap going forward. Desktops will commonly have 10 gigabit Ethernet connections to desktops or workstations with 100 and 200 over the network, and even 400 gigabits are available at the switch level. So it's going to have a very robust, very long roadmap going forward. And what, to me, is one of the more important things is when you look at your next generation applications, and we'll talk a little bit more about this as we go forward. When you look at those next generation applications, one of the things that's really important is the ability to use object storage, whether you're doing that to store data in the cloud, or you're looking for local high performance S3 object storage. And again, we'll talk about that. Fiber channel isn't directly compatible with that. You'll have to do some type of conversion to move that data to be compatible with object storage. Ethernet is completely compatible with object storage, so you don't have to make that conversion. So it's going to save you a lot of time, money, and effort going forward. Would you agree with that, Keith?
Absolutely. I think, coming at it from a storage architect design side of it, I always want the flexibility to, in any even in the last couple of years, any design that I'm putting forward has to be able to get data in and out of the cloud. Or the cloud, multiple cloud providers, so I'm always looking at that as one of my key metrics that I have to be able to imagine that landscape is going to include some form or fashion of a cloud service. And then I also have to think about, obviously I don't want any roadblocks in my architecture. I want to be able to go as quickly as possible with economies of scale. So Ethernet is really, laying a great foundation for the future. And so I agree, the NVMe over TCP seems like the right path for most of these designs.
I completely agree. So with that, let's go ahead and talk a little bit more about RDMA. So RDMA, when used with Ethernet, is something called RoCE, R-O-C-E, or RDMA over converged Ethernet. And essentially that's just a way of saying that we're doing RDMA over the network. So one of the things to look at is when you look at storage arrays, and this, I can't really overstate the importance of this. When you look at storage arrays, one of the key components, especially of an all-flash array, that vendors talk about is the latency they're able to provide. They talk about providing low latency, and that could be, that could be any type of all-flash array, whether it's NVMe over fiber channel or just plain fiber channel, or even just with straight TCP without RoCE. When you get that measurement of latency, what they're talking about is they're talking about the measurement of time that occurs from the time the storage array receives the IO request until it puts that IO request back out on the wire. So it's the ingress of the request at the back of the array and the egress of the fulfillment of that request out the back of the array. So all that latency is strictly within the storage array. So you'll see an all-flash array will say, sub-millisecond latency, or maybe even 500 microseconds of latency. That is the latency that occurs within the storage array itself. When an array vendor such as, or a storage manufacturer such as Pavilion talks about latency with RDMA, and we do segregate it depending on which protocol we're using. When you're talking about RDMA, we're talking about a very different measurement. We're not just talking about the latency within the array. We're talking about from the time the storage array receives the request up until the time that data is actually put into system memory of the host system that's making the IO request. So we're not just talking about latency within the array. We're talking about latency within the array, back out over the network and into system memory so it can be used by your applications. So that's the thing to look at with NVMe, with OF, with Rocky. Pavilion is able to provide extremely low latency of as little as 25 microseconds, and that's significantly, 20 times less than many other storage arrays out there. But it's not just less; it's less over a greater distance. So we're faster, further. So that's something to go ahead and consider when you look at different storage arrays, specifically with NVMe-oF. So just because it's NVMe-oF, not all is equal. So NVMe-oF over fiber channel, which does not support RDMA, or NVMe-oF over TCP without RDMA, or NVMe-oF with Rocky, which is with RDMA. Those are some of the different things you want to take into consideration when you're looking at an NVMe-oF implementation. All right. And so I guess the question is, what kind of applications are really driving the need for this type of solution? What really needs that extreme high throughput and low latency of NVMe? Well, when you look at the way applications are evolving, one of the things you look at kind of a scale out our infrastructure. For a long time we've had virtual systems using VMware or Hyper-V or Zen server, whatever your virtualization application of choice happens to be. And that was fine for scale up, but now we're looking at scale out applications using Docker and Kubernetes, things where you're creating different containers on the fly and you need to scale your infrastructure and you'll have thousands of containers trying to access data simultaneously. These are the kind of things that are driving the need for that kind of high performance. And it's not just your infrastructure, it's your applications. If you're using big data solutions like Hadoop, you've got high performance databases such as Greenplum, or maybe you're doing some AI, you're doing Elasticsearch, you've got Apache Spark, you're doing SQL Server. Whatever these scale out applications are, they need to be able to access massive amounts of data in parallel to really deliver on what those applications can produce. And to do that, your storage needs to be able to provide consistent, predictable, scalable, high performance with low latency. And beyond that, your servers also are going to be scaling out. So, the server, the compute processes are going to scale out. So people are going to be able to add compute nodes, on demand as they need more performance. It's going to add nodes and add nodes. So those servers are going to scale out. So shouldn't your storage also scale out? You've got hyper-parallel infrastructure. You've got parallel applications. You've got parallel servers. Well, now your storage can also be parallel. And what do I mean by parallel? I mean, you can have an array that has not just dual controller architectures, not 2 controllers, not maybe 4, but 20 controllers within a single for you array. Each of these controllers can provide extreme high bandwidth, up to 40 100 gigabit Ethernet ports or InfiniBand ports, supports multiple protocols, NVMe, NVMe-oF, we support TCP, iSCSI, NFS, and we support block, file, and object protocols on each of those individual controllers separately. One of the key things to look at when you look at a multi-protocol array is typically when you look at one, you're going to get an array that supports, for example, it supports file natively. Well, and then they've layered object on top of it. So you've got object running on top of file. So you've got those different protocols intermingling, which is going to go ahead and reduce your performance often significantly because of all that extra overhead that's involved in that. We don't do that. And as far as I know, we're the only ones that don't do that because we allow each of those protocols to run natively on each controller, providing extreme high performance for block, extreme high performance for file, extreme high performance for object, natively and individually. Wouldn't you agree, Keith?
Absolutely. I think this is a space where it's fun to see this laid out at a high level with these different applications, which we see every day in and out. But I like to kind of dig in deeper. I like to get my hands dirty. So I like to dive in and talk to kind of how things actually integrate more at a ground level, at a file system level, how that kind of breaks out. Because, talking about the applications, it's good to connect it all the way through the stack. And starting there is a great great starting point for us.
I totally agree. So with that, I'd like to ask you, maybe if you could talk a little bit about, what are some of the different ways that people could go ahead and implement an NVMe-oF solution into their data centers?
Oh, thank you, Keith. I see this as four, key design or major design categories. And, I'll kind of work from the top left. If you think about it, high performance parallel file systems are typically found in the high performance computing space, with the usual suspects in play. I think of IBM Spectrum Scale, or more commonly referred to as GPFS. There's also Lustre and newcomers such as BGFS. All of these have a parallel file system advantages. Think of parallel performance for large HPC systems, and I'm talking about hundreds and thousands of servers. These architectures are designed to have high throughput for even a single client. They have low latency networks. This is your InfiniBand networks in the back. In many cases, if you think about the application stack, these are really built around streaming high performance data. Now, the applications, this ecosystem, I believe, continues to evolve. And I see this, you talked about it in the previous slide about how there's big data projects such as Spark, Hive. There's databases like MongoDB. A lot of these workloads, when you start to look at it, are highly distributed. And this is a case even for more modern applications such as AI, where folks are looking at machine learning and deep learning. If you think about it, instead of a scale-out CPU architecture, these are going in a parallelized GPU architecture. And this is really lining up for the growth in the high-performance computing market. And in many cases, this is a good fit for those application stacks. If we slide over to the top right-hand corner and you think about shared data, commonly we use the network file system or NFS. And there are some, again, inherent advantages with this design, namely simplicity. It's the de facto standard for anything shared on Unix systems. Low cost, I could stand this up on any Unix server or Linux server in a minute once I download the right packages, right? This is also being leveraged for a lot of cloud and IoT type use cases. One of the things I've done in the past is I've run a number of web services. So I ran web services for a large government agency where I would deploy Tomcat and Apache and things of that nature. Again, NFS was a great, simple use case where it fit the job. It was also the backbone for a lot of the genomic sequencing I did when I was at the National Cancer Institute. Highly parallel workloads, but the performance wasn't quite to the watermark of needing a parallel file system. A lot of times you can get away with that with NFS if it's fast enough. But I want to keep going. There's several different designs out there, and another of those that's kind of interesting is that direct attach. Again, it's the simple button, right? I started out, I bought a server, I needed a database, was often the easy answer for me was to directly attach drives into a large server that would run critical databases for the institute that I was working at, or MySQL databases. I didn't have to worry about a network outage causing a loss of connection to something. But those were years ago when, architectures were much more disaggregated and not as resilient as they are today. And this architecture has become the backbone for a lot of, again, big data projects, as well as like cybersecurity and near real-time workloads, is this scale-out design. The last one I'll mention is really on the object storage side of the space. I think of cloud native and Keith, you know about this. I've worked for hybrid cloud technology companies in my past. One of those was acquired by Microsoft, so I certainly understand the value of being able to take advantage of cloud where it's accessible. And the cloud has massive scaling and massive storage capabilities. So there are inherent advantages of leveraging an S3 API, and I'm talking to the API level of this, where you can write the data and have metadata tagging. The cloud providers and object storage capabilities give you great data security. Everybody gets their own unique ID that they can access this data. And each of these designs has various valid application use cases. Keith, wouldn't you agree?
I absolutely would. And each of these has their place. And depending upon your environment, depending upon your applications, depending on what you're trying to achieve, you're really going to want to look at one or maybe several of these within your data center. Maybe we can take a little look at how each of these are applicable to different workloads and why different people might want to use them and how NVMe-oF can really enable them.
Oh, that's a great segue. I think if we dive in, if we jump to really the parallel file systems, I'll start there. And if you think about it, I talked to the highlights of parallel file systems, but there's also some very real challenges out there. And I'll give you some idea of what those challenges are that people run into. As an example, deployment complexity. This is really at the top of the list. If you're starting from scratch for a parallel file system, this is the heavy lift. Certainly, people struggle getting these types of architectures off the ground. I've done it in the past, and it's not as easy as standing up that NFS server, as I mentioned before. There's also the added cost. So you go into this architecture, and now you have to pay for the IBM, the BGFS, the licensing that goes with some of this. And not only is it a cost thing, but these HPC designs were often tuned for a particular workload, be it streaming throughput, or if you had a use case where you needed something that was randomized, you might create a special queue, you might create a special storage target that was tuned for this very specific use case. Now, this is where it gets interesting. If you think about it, this is where NVMe over Fabrics begins to start to unravel and solve some of the problems that are inherent to these large parallel file systems. So if you look at it, NVMe over Fabrics can reduce the complexity. It can be a shared storage system that it can even come in and remove an entire layer of servers, simplifying the design. And you might ask, how is this done? I'll give you an example. With GPFS, we can remove things like the NSD servers, which would be the storage server in that architecture. By doing so, we remove a hop in the data flow. And not only do we reduce the number of servers you need to actually implement this, we deliver higher performance as an added bonus. And let's not forget, by removing all those servers, you're actually reducing the cost of your overall system and architecture. So I like to say it's doing more with less.
I totally agree. And it's not just a function of reducing servers. By taking those out of that equation, what you're doing is you're reducing your cost, you're reducing your complexity, you're reducing the footprint you're taking up in your data center. You're really cutting down on all the extra work and expense that goes into managing one of these. And you're doing it while simultaneously increasing your performance, sometimes dramatically.
You're spot on, and reducing that footprint, typically in a parallel file system, these are the architectures where you have a row and row of spinning drive architectures, and they do serve up the data in a streaming sequential format very well. But again, if you have any type of new use case, I think 2020 is one of those great years where I stress with other engineers that I've been working with is like, don't design it for just this very, very narrow use case. Without giving yourself some options, because you never know. I was always surprised by the scientific community because they always kept me on my toes. I would expect, they always gave me a number at the start of the year. Hey, Keith, we're going to grow by so many terabytes per year, or I need this much compute, and this is the goal for the entire year. And 3 months into it, they come back and say, well, things have changed, and now you need to double this, or I need 3 times the compute. I like the idea of having that flexibility built in. And this, again, is where NVMe over Fabric, it reduces the need to do all this tuning. I mentioned how you might want streaming throughput, or you might need random processing. Well, this is a case where leveraging NVMe over Fabrics and the NVMe drive and having that low latency, you have the ability to not only do streaming throughput, but you can deliver millions of IOPS with a very small system. Imagine a 4U appliance delivering millions of IOPS to your end clients. At the same time, the system can do 100 gigabytes per second of read and 70 gigabytes per second of write. Tremendous amount of potential for your environment. And honestly, it's a lot easier to manage that way. Would you say so, Keith?
I absolutely would, and especially when you look at what some of these environments are doing. One of the new workloads that you were seeing in a lot of these are really AI and ML workloads. And it's not just CPU driven systems, but GPU driven systems that really need parallel performance, that have more queues within the processors, that have more data flows. So being able to provide that data to them in parallel is really the only way to keep those processors, those CPUs, those GPUs, really keep them fully saturated so they're actually doing what they're supposed to be doing.
Absolutely.
Okay. Well, maybe we can talk about some of the other implementations that people will be using. For example, let's talk a little bit about network file systems.
Haha. This is one of those ones that I really enjoy. This is an area where I leverage network file systems or NFS for a lot of workloads in my past. It also doesn't mean that I haven't hit the performance wall, and I've certainly done that as well. There's a lot of advantages, but at the same time, the disadvantages, things like limited throughput. This is especially true from a single client. So be careful with the fine print when you're looking at these storage architectures out there. A lot of times you'll see in the marketing details, these really high throughput performance numbers. But then when you start to peel back the details and you bring it in-house and you do performance benchmarking on it, and you'll find out, oh, I thought I was getting gigabytes per second of write speed. And in reality, even the high performance ones, they're talking megabytes per second. Again, it's in the fine print, right? This is coming up repeatedly in my discussions, particularly, Keith, as you mentioned, the AI ML type use cases. This is coming up where people have taken, and if you think about it, the new DGX A100, I believe it's 5 petaflops of compute power in a single system. Even the older DGX ones, they were a petaflop in one system. That's a massive amount of parallel computing that you can run. That's essentially an HPC center in a very small footprint. And those types of architectures, they're running into this single client throughput limitation. I joke about it being the performance wall, because you have all these GPU cores waiting for data, and you fire it up and say, okay, pull in the data, and now all of a sudden you're not getting response back, or you're limited to megabytes per second versus gigabytes.
I totally agree, and that's really the big thing with this protocol and these types of solutions is it's not the performance that's coming out of the box. It's the per client performance that it's able to provide. How many workstations are accessing this, and what's the performance they're getting. That's always going to be the limiting factor in this particular type of implementation, and that's really what held people back from doing the things they wanted to do with NFS storage.
Absolutely, and NFS works well for an all Ethernet architecture. This does play well into your cloud providers, which you might be running different file services and migrating data back and forth across Ethernet architectures. But if you think about your data workflow, it does create challenges if you've got multiple hops in this architecture. And being able to, not only that, but you also have the load on the compute cycles. So if you take those into account, one of the challenges that you can also run into is really that latency from the client. And that latency isn't necessarily always tied to throughput. I talk about throughput, the performance wall I typically talk about is the performance one, but there's also the latency. So if you've got an application that's sensitive on how quickly the system responds, this could certainly bubble to the top and be one of your leading challenges with an NFS architecture.
Yeah, and some of those key applications can include things like any kind of high performance database, any AI and ML type of workloads, any type of IoT workloads. These are so many of the things that people are trying to do going forward, that it's not just a function of throughput, but latency that really impacts their overall results.
So one of the things that I think is interesting, we're talking about NVMe over fabrics, and we're talking about how this really benefits, architects in designing the next generation of applications. Keith, you mentioned about NVMe over Rocky. Could this play a factor in NFS workloads and potentially offer some benefits in that space?
Absolutely, because that's really what Rocky is designed to do, is reduce that overall latency. It cuts down on the protocol overhead. It cuts down on the processing that has to happen to it. And because it's able to place data directly into system memory of the application that's requesting it, it can dramatically reduce the overall latency. And that's so key for some of these applications going forward.
Well, and if you think about it, not only now, if you're able to drive down the latency and you now have the ability to deliver even with small file accesses because you've driven down the latency requirement to a really low layer, the ability to connect at a controller level, some of these architectures are coming out with 100 gigabit Ethernet networks attached. You know, this type of connection, and this is where it starts to bleed over, and this is where it's fun as an architect to go, okay, you know, NFS can do more than I ever thought it could. You know, you've moved that performance wall, you know, another 100 yards out, where, you know, if you've got 100 gig connections, you've got low latency through Rocky. Now all of a sudden, NFS looks like an HPC level of performance in many cases. You know, this is where you can scale into tens of gigabytes per second for read and write at an NFS level. Those numbers start to sound like HPC or parallel file system levels. Don't you think, Keith?
Absolutely, and that's so important for organizations that have workloads where they're going to be using, you know, large files. You know, let's be honest. That's what NFS is really good for, is big files. You know, it's for you know videos. It's for things where people are going to have, you know, large pictures, where people are going to have big files that they need to move. And by able to doing it with high performance, being able to do it with low latency, that's really going to help those applications.
Absolutely.
Okay, let's go ahead and take a look at the next different layout, if we could.
Sure. So the next one I'd like to talk about is kind of this direct attach model. So everyone gets the simplicity and performance of this, but then again, there are always challenges. This is where, again, NVMe can solve some of these major challenges that run in this space. So when I think about local disk, you're really limited about capacity. When a system runs on a specific space, it can be very difficult to problem solve, you know, especially in a year, you know, as I mentioned before, like this year, 2020, where there's all kinds of unexpected demands being put on engineers across the globe. You know, how do you solve this when suddenly your data has grown, or maybe it's the data ingest speed has increased? This is really difficult if you're talking about a truly direct attached storage architecture. Thankfully, NVMe over fabrics can provide some amazing advantages. Imagine servers or VMs with a flexible capacity option with linear scaling. So you can deliver direct attached levels of performance, as Keith mentioned earlier, at the same time, the latency at both ends for read and write delivered to that end client. This is actually how, you know, when I think about it, I go back to put on my hat where I'm looking at multi-cloud architectures. This is really how the cloud providers have been provisioning architectures for a while now. If you think about EBS and Amazon's AWS, the volumes that are leveraged for these EC2 instances, they're flexible. When you boot up, you provision how much storage you want attached to that. If I take this a step further and I imagine where things are going, if you think about Kubernetes environments, could you imagine leveraging NVMe over Fabric volume directly attached within your Kubernetes pod? I'm actually helping build architectures today that come with, you know, that come with these types of building blocks that people want to understand how to do this. You know, this is a great opportunity. I think that my team here at Pavilion, we're talking to folks, helping them build these types of architectures, which I think is really an interesting space to leverage. I love connecting people with the right technology pieces to go out and do things that have never been possible before. Do you see the same thing, Keith?
I totally agree. You know, when I look at direct attached storage, which, you know, I'm an old SCSI guy. I've been doing this for a long time. And I look at the progression that direct attach has gone through over the years. 20 years ago, people started getting away from a direct attach model because of all the limitations it had. It had limitations in terms of scalability and reliability and availability and all the illities that you just couldn't do with direct attach. People moved to more of a storage network model, which solved a lot of those problems, but it introduced performance issues. Storage attached networks were never able to match the kind of performance you were going to go ahead and get from a direct attach solution. So there was kind of a swing back of the pendulum, if you will, to a direct attach solution where people are, doing that cloud model that the cloud providers are doing, where you're, using the whole compute node as a building block, and that allows you to consolidate and do direct attach. And you need more capacity, throw in another node. You need more compute, throw in another node. And that allows you to really scale your infrastructure. Everything becomes easy. It becomes highly scalable. It becomes flexible, but there's still some drawbacks there. One of the challenges is, well, if you need to add capacity, well, you add another node, which means you're adding compute. You need to add compute, you're adding another node, which means you're adding capacity, whether you need it or not. So from that perspective, you're going to be spending a lot more on one of those resources that you just don't need. It's also going to have a lot of inherent overhead. The way this is all managed is through software. And that software is going to take up a lot of those processing cycles that you're adding. So every time you add compute to your direct attached nodes, well, you're going to be consuming some of those compute cycles with overhead and management. So by being able to disaggregate the storage from those and still have the ability to scale those nodes, to still add processing power, whether it's CPU or GPU driven, and have that storage be independent while providing the same kind of performance, that's truly incredible. Because when you look at NVMe-oF, it's providing the same or better performance as those direct attached drives. A direct attached NVMe drive is going to be, 20, 30 or so milliseconds of latency. Pavilion NVMe-oF with RDMA, with Rocky, is also going to be 25 milliseconds of latency. So you're going to get about the same, and in some cases better performance, with all the scalability, with all the flexibility, with all the availability that comes from that disaggregated storage. So you're getting all those benefits of the SAN, and you're getting the performance of direct attach all at the same time. And that's, to me, that is such a game-changing solution that people can now run those high performance workloads. They can run their AI and ML workloads. They can have access to those large files so they can do their learning on their AI models. They can do the things that they've always wanted to do, and they can do it in a smaller footprint that's more flexible and provides higher performance.
Yeah, and I can just add to that one more aspect, one more dimension to that topic is, if you think about the bare metal architectures today, and the building blocks. I had a whiteboard session with somebody not that long ago where they were talking about the impact of, as an example, the AMD new processors and the number of cores that they're going to be able to pack into an individual server. The compute power has doubled essentially in each one of their servers for their next generation, which is disrupting the direct attach model that they've been using in the past. And they recognize that they no longer want to, they don't have enough storage in a compute node to really match the compute power that they have. And so they're like, this direct attach model, this DAS model needs to be broken apart, because I have so much compute pent up in my servers that I need more storage to feed them. And so this is true, especially true for things like the Kubernetes stacks and these large deployments I'm talking to folks about. They're like, I need to draw a line down the middle. I need to have compute on one side and I need to have storage on the other. And I think that's this place where NVMe is the right technology at the right time to solve some of those really interesting challenges. And Keith, you and I, we're right in the middle of that. We're knee deep in this transition that's happening in the marketplace today.
I totally agree. And speaking of transitions, I'd like to go to the next storage model, which in and of itself is going through a major transition, and that's object storage. And this to me is one of the most important ones, because as you look at applications today, they really are moving to an object storage model, the ability to take advantage of S3 storage. Maybe you can talk a little bit about that, Keith?
Absolutely. You know, so I'll take it from a different perspective. So I recently spoke with a true thought leader in the high performance computing market. And he said, you know, if he had the option, he would write every single bit of data into an S3 object format for all of his applications. The problem is that not all of his applications have been ported over to support an object storage or an S3 API driven model. You know, and I think there's a lot of validity in that line of thinking, because if you think about it, if you're ultimately going to take advantage of the size and scale of these cloud providers, it does make sense to keep the same format from source to destination. And a lot of times, if you're going to build this architecture, you want that initial collection to be high performance. This is one of the challenges, honestly, that's pervasive in the market, is the storage options in the cloud are relatively performant. But when you get on premise, you know, these same architectures are drastically slower than what you get in Amazon or in Google Cloud. So this is where, you know, NVMe is coming to the rescue. So if you think about an architecture where you've got the back end is these NVMe drives, as Keith illustrated earlier, with all these queues, if you front end that with something that can speak S3 API calls, now you have something that is able to come in and, you know, potentially deliver the type of performance that you'd see in a high-speed NFS architecture. If you could get high-speed NFS speeds out of an S3 object store that you put on premise, wouldn't you want to take advantage of that? What do you think, Keith?
Yeah, absolutely. And I think that's especially true with, and again, I'll go back to the AI and ML models, and especially with deep learning, as you're using, in some cases, millions of objects to train your models. Having the ability to access those in a performant manner is just so critical to the success of those models. It really fundamentally changes what you can do.
Absolutely. And you even have the ability to add, you know, with things like custom metadata, you have the ability to have additional curation, data processing that you can do against that same data set. And you know, we're just starting to get into the point where Amazon has recognized this. They're taking advantage of this. But if you could do this in real time, on premise, collect that data and do that processing before you send it to the cloud, that's where you hit the real time workloads. And, you know, it becomes a very interesting space.
And having the ability to do that locally with ultra low latency to do your learning models, and then put that data, once you're done with it, put it off into the cloud in its native format. You know, that's one of the things that's great about the cloud. If you're done with your data and you want to hang on to it, you can put it in the cloud and you can store it there pretty much forever. It's pretty affordable. You know, the challenge is bringing that data back. If you have to read that data back, that's where it gets expensive. That's where those cloud providers are paying for all those data centers. So by having the ability to use the data in an S3 format locally, with performance, with low latency, and then store it in the cloud for archive, that's the perfect combination. That's kind of the goal. Okay, and with that, you know, we just want to talk briefly about how innovation can enable flexibility in each of these environments. When you look at the HPC environments, when you look at the scale and the need for parallel data access, because you have all those CPUs, all those GPUs really needing to be fed by data, being able to provide that in a parallel format in a high performance, ultra low latency method is so critical. When you're looking at doing it with scale out NFS, by being able to provide high throughput using NVMe-oF as the underlying transport to some of these 100 gigabit Ethernet connections, you're finally able to deliver those per workload, those per workstation performance numbers that you're needing. You're going from, in some cases, you're going from megabytes per second to gigabytes per second, sometimes double-digit gigabytes per second of performance. And that's just a complete game changer in things that were simply never thought possible with NFS before. When you look at the direct attached model, and you're just able to disaggregate that storage from there and provide the same or better performance than you were getting in a direct attached model, while still enabling the flexibility to scale your compute, your processing nodes on demand, that unleashes what you can do with your processing and your applications at that point. And going forward, as applications become more native in terms of S3 access, having local high performance, low latency S3 object storage on premise that you can then stream off to the cloud for archive, that's really the goal. That's where we need to get, where we have that ultra high performance, that millions and millions of objects that can be stored locally and then stored remotely. That's the goal we really look forward to getting to. And with that, I just would like to take one moment talking about the Pavilion hyperparallel flash array, which is really able to deliver the performance, the density, and the throughput that these applications need. I talked about the fact that we're able to support block, file, and object all simultaneously from each Pavilion hyperparallel flash array. That means whether you're using a parallel file system, whether you're using direct attach, you're using it through NSD servers with Spectrum scale, you want to eliminate your NSD servers with Spectrum scale. Whatever you want to do, the hyperparallel flash array is able to provide that. It's able to provide that NVMe-oF underlying performance for your high performance NFS workstations. It's able to provide block level storage to your direct attach models, and it does have native S3 support, all simultaneously, all with high performance, all at the same time. It's able to provide that in a very compact system. It's a 4U solution that contains 20 independent controllers and up to a petabyte of usable capacity. Again, in each 4U solution, it has 40 100 gigabit Ethernet ports. Yes, 40 100 gigabit high-speed Ethernet or InfiniBand ports out the back. So you're able to deliver that high performance, that ultra low latency. When I talk about performance, what am I talking about? I'm talking 20 million IOPS of read performance from a single 4U solution with 120 gigabytes of sustained read performance from that solution. Now, to deliver that kind of high IOPS and that kind of throughput in that much capacity, you're typically going to be looking at, a rack of storage. You're looking at 2 racks of storage. You're looking at, best case, you're looking at 20, 40 racks of flash to deliver that. And we're able to do that in a 4U footprint. And we're able to do that with latencies as low as 25 microseconds. So that's one Pavilion hyperparallel flash array. What if I have that scale out architecture where I need, even more capacity, I need to grow? Well, that's where we're looking at we're looking at our rack scale solution. So up to 1.2 terabytes per second of performance per rack. Yes, that's terabytes with a T. 1.2 terabytes of performance from that rack. We're able to deliver 10 petabytes of usable capacity, 200 million IOPS, 1.2 terabytes of read performance. This is the kind of solution that we're delivering with NVMe-oF in production customer environments today. And if you'd like to learn more about that, I encourage you to reach out to us. And at this point, I'd like to go ahead and open it up to any questions. If you do have questions, please feel free to go ahead and put them into the chat function, and we'll answer them as quickly as possible. Looking at it right now, we do have a couple of questions that have come in. And the first question, it says, for block storage, I use iSCSI today. How would I migrate my current architecture to an NVMe-oF? Keith, do you want to go ahead and take that?
Absolutely. So, I recognize not everybody has the infrastructure today to take advantage of the NVMe over fabrics. You're typically looking at newer network client connections and things of that nature. But, I was recently talking with a customer where their infrastructure is currently all iSCSI. And as an architect looking at the future, you can take iSCSI and then migrate that to NVMe over TCP or NVMe over fabrics later on as a way to future-proof your design. So we do support that today with our architecture, but if it's all built around an Ethernet architecture, you have the roadmap and the ability to get there down the road.
Great. Okay, and the next question that came in is you said you have 40 Ethernet or InfiniBand ports on the back, does that mean I can directly attach my server in a rack of servers to that as opposed to going through a switch?
So actually, that is a possibility. Typically, customers would want to connect this into a network switch of some kind. But I have talked to some customers, and I've done testing around this where there's some interesting use cases where people have, as an example, a case where somebody wants to collect data in real time and do processing against it. This would be one of those cases where maybe it might make sense to directly connect it if you've got a fixed sensor or something that you're trying to ingest. I think scientific computing, there might be some use cases where that would make sense.
Okay, great. And I have one more question that's come in, and it's asking about using the fiber channel protocol for bank customers. Is there a use case for that? And and feel free to chime in, Keith. I would probably respond that, fiber channel, a lot of, especially a lot of banks have been using fiber channel for their storage networks in the past, and there is absolutely a path to use NVMe over fiber channel for that going forward. What I would suggest is looking at what those customers want to achieve in terms of security, in terms of reliability, in terms of performance, and really compare and contrast whether you want to continue with the fiber channel protocol or if there's a path to using NVMe over TCP or with Rocky, and because that's really the next step in storage networking is using that Ethernet protocol, because it does provide the performance, the ultra low latency, the high throughput that quite frankly fiber channel is not really going to be able to achieve, and it's able to do that for scale out architectures. And we do have a number of financial customers who are using this for is extremely sensitive financial information like a bank customer might use. I'm not sure what the details of this question are, but we actually put out a press release today with a customer that's using it for financial information. Okay, and it looks like we are about out of time, so unless there are any other questions, all of you who did attend, we will make this presentation available to you on demand, and thank you very much.
Yep, thank you.